Guys, gals, and fellow gender non-conforming pals, welcome back. My legal name is C28. And we had a pretty cool lab this time as well. This lab, which happened yesterday actually, shooting this log later because I went out partying. Yeah, we had a cool little karaoke thing happen, and that was pretty cool. But I don't know if there's it. I think that's about all there is to say on the karaoke, that it happened. I don't think there's much else to say, so that's probably it. There's a show pro event. But the lab, we were working on soldering now. So I am officially understanding how to do soldering. That's fun. Indeed, indeed. I think I've done it before in the Boy Scouts, back in the when I was still vibing as a boy. Gender norms, gross. Anyway, yeah, so we did some soldering, and specifically soldering, what are they called? Oh my goodness, on screen now, that thing. I'm not quite happy with myself if I don't get the name of this, so give me a minute, let me think of the name. Okay, for my own pleasure and nothing else, patch base, that was the word that was on screen. We figured out how to, we were taught how to solder patch bays. So your TRS cable, all that. Sorry about that call. Actually, that didn't go through. I forget that I'm using a noise gate, so you can only hear stuff when I can hear it through the headphones. So if I do something like this, you can't hear it because it's not being picked up. But if I do this, oh, now you heard it. Yeah, gate, magic. Not really magic, but still. So the TRS connections, tip, ring, sleeve. And seeing the internals, that was really cool. So we started with just having we were provided with one wire. And with that one wire, we had to strip off the ends of the insulation. So we would reveal just the raw wire itself, twist that up so it stays in place, and then we go ahead and begin the soldering process. So to solder to tinning it. So we aren't soldering it to anything yet, but we tin it first. Tinning is just the process of putting solder on the thing to prepare it to be soldered. So it's kind of like adding glue before you glue something, which doesn't make sense, but in terms of soldering it does, because solder is stupid good at sticking to itself when it's molten, and really good at not doing that when it's not. And it doesn't have like a super long cool time. What it was called. It melts and crystallizes back into solid form really quickly. And it's like, once it hits this threshold, the whole thing goes and it goes over. So you gotta be quick with it, and you have to make sure that you're not letting the whole thing just bundle up in one area. Lots of soldering things I'll learn down the line as I get better at this skill, but yeah, so we tinned after we stripped off 2 ends of the wire, and then we broke the wire intentionally so then we could solder it back together. So we cut the wire in half, and then now that it was cut in half, we stripped those ends together, tinned those together, and now we did the magic bit. We soldered the 2 ends together to show you know how to repair a cable if it breaks. So yes, so you lay the thing on top. You lay the thing on top, one end of the cable, all on top of another end, the other end of the other cable that is now 2 because you cut them in half. And you apply a little bit of solder on top of your iron. You tin the iron, and then you put a little solder on there. You let that touch, you let that melt, and you quickly get off. So you have a nice continuous thing of a soldered wire. Then we put some heat shrink on it. Allow ourselves to let that heat shrink shrivel up, grasp the wire tightly. And then we've repaired the wire. But it's not very useful at this point, so what we did next is we attached alligator clips. That part was a bloody nightmare. I still don't think I did it quite perfectly. But actually I can get my alligator clips. I'll show you after I explain it. So I'll explain it, then I'll leave my, I guess you could call this studio, but it's like a corner of my room. My studio corner, pick up the cables and show you. But we had alligator clips that we had to attach on. So the process for that was pretty straightforward. You loop your wire through one of the holes. You put some solder on it so it can't slip through that hole. That's good. Yeah, you're set. Now, there is some insulation for that, so you have to put those on first, so that way you can slip them on, because it has like a thick end and a tiny end, or a large end and a small end. You're not going to fit the small end over the large end. It's not happening, mate. You're going to break it. So put those on first, then put the things on, solder them, then you're good. And eventually you get a product that looks like this. Yeah, so this is my finished alligator clip situation. Look at it in all of its glory. Now look at me. Now look at it. Now back to me. Now look at the microphone. Lots of stuff to look at. That was stupid. I don't know why I did that. But you can see here the repair that was made. I think this is the wide angle camera. I'm not sure, but it's one of these three. And you're bound to see it at some point. So that's the joint connection. And then if I peel this back, you should be able to see the soldering work that was done on the terminal of the clip itself. Come off, oh my goodness. You had to close them so it would, yeah, let you. But there's my soldering work. It's not outstanding. It's just like a little bead of solder on there, not letting it go down, but it works. And it attaches the terminal nicely. Then you bend in the sort of, I guess, what do you call those? Teeth, bend in the teeth to hold the wire in place. Yeah. I put it back together. Should probably attach it to something so it will easier to do. Let's see. Yeah. And the same on the other end. So alligator clips, we made those, so we know how to make that very basic thing. Can be very helpful and come in handy. I might put these in my side bag that I usually wear on me. I don't tend to wear it in my video logs anymore just because it's heavy and it's nice to be able to put it away when I'm not outside. It's like wearing a backpack inside your house. Why would you do that? So yes, we made this today. Or not today, yesterday. We made it yesterday. Okay. And we also soldered the, oh my goodness, I've forgotten the word again. What was the word? Patch bay. We also soldered the patch bay jacks. So I have a video of that showing the solder work that was done. But essentially you have your ground, your high and low, and those three wires need to be soldered on the little prongs coming out of the TRS port. So here's that video.
It's got pictures and everything.
Oh yeah, but back to the mixed critique.
Yeah. Which has happened 3 times in my life.
Oh really?
Yes, 3 different times. That's
Okay. All right, no problem.
And so you see that's what it looks like. Some ambient background speaking and noise and stuff because there's no gate like there is here. Or if I go to, you know, the dog that's barking right now, doesn't reach the decibel requirement. No entry, mate. I love the gate. I love the gate. It's so nice. So nice. I wish I started making my video logs with this high of a quality, but then I wouldn't get to where I am now, I suppose, because I just wouldn't have started. It's funny, it turned into just the whole production. Yeah, so that was lab was that. Making those 2 things. So getting our basic soldering work done so we can, our basic soldering skills initiated so that we know what to do in the future when we are soldering stuff using heat shrinks and getting pretty tight solder work done. As you saw, those terminals on the TRS port for the patch bay is they're pretty tight. Not a whole lot of room for error. Don't want to bridge those and short them. Yeah. In lecture, we did a little bit of a different thing. In lecture, we were going over equations on how to calculate reactants. And so 2 types of reactants you'll have are capacitive and inductive reactants. I'm going to need to pull up notes, which is why I've started this video log with my computer this way, so I don't cheat wholesale out of their material. So yeah, let me see how to explain what we were doing. There we go. So inductive reactance is measured in ohms, same as capacitive reactance, same as resistance, and same as impedance. They're all measured in ohms. And inductive reactance is measured in ohms, the impedance of a reductor. Inductor. Reductor. Inductor is what it is, not a reductor. Not a thing, I think. And that increases as your frequency increases. So the calculation for that, the formula, is 2 pi times the frequency times the inductance, which is measured in henries. So, yes, and typically you're going to have this in millihenries. So it's important to know how to convert from millihenries to henries when you're doing the equation. So, you know, if you have something like 75.39 millihenries, it's not 75.39 henries. That's a lot of henries. Whoa. So, you know, what's it called? Decimal values matter. Sorry that word just evaded me. The other type of reactance you can have is capacitive reactance. And this will decrease as your frequency increases. So your capacitive reactance is measured very similarly, but slightly different. So it's 2 pi times frequency times your capacitive, your capacitance. And here's the thing. Under 1. So it's the inverse of that. So you use that little flip button on your calculator that I showed you last time. And that is how you get capacitive reactance. Now, total reactance is a little different now. This is the more useful thing. So why do you even want to calculate these things? Why do it? Well, here's why. In capacitive reactance, you're going to have... Ooh, I'm going to roll some dice, and I think I'm right. I'm not going to roll dice. Let's not roll dice. Let's figure it out for sure. BRB. Okay, so got the answer. In a capacitor, your voltage is going to lag behind your current. So, also great. You have a differential there. The inverse happens in an inductor. You're going to have your current lag behind your voltage. So the two of them do some of that stuff together, and that cancels out. Of course, if you have one lag behind the other does the opposite, well then you got to calculate. And you can probably guess the equation's pretty straightforward. You're subtracting one from the other. So what you're doing is you are subtracting your inductive reactance. Correction. You're subtracting your capacitive reactance by your inductive reactance. And that gets your total reactance, which is the total amount that your current is lagging behind your voltage, or vice versa. And it's important to know the difference. So that's why this number can actually be negative. This can be a negative number, but it's getting the absolute value of those two. So you understand the, what's it? So you're getting the absolute value of your inductive reactance minus the absolute value of your capacitive reactance to find out total reactance, which will help you with other things down the line. And those other things down the line are boom. Getting your impedance. So you get your reactance, you get your resistance, and you can find your impedance. So impedance follows the same formula you might be familiar with for a right triangle. What equation do you think we're using for that? That's right, good old Pythagoras. So you take your resistance squared, your reactance squared, and that will give you your impedance squared. So of course get the square roots of that and you'll get your true impedance. So example here, if you were to have something like a resistance of 50 ohms and a reactance of minus 208.35 ohms, something like that. You would then square your resistance, so you get 2,500 ohms. you would square your reactance, which gets you 45,409.72 ohms. And then you add those together for a total of 45,909.72 ohms. And finally, you get the root of that for 214.27 ohms of impedance. Yes. Lots of mathematics. I promise you that'll be the last maths thing here, going through the whole problem. I'll just explain the equations from now on. But yes, so to get your impedance, the whole formula is a little tricky. Your impedance is the root of the following: resistance squared plus the function of, first, 2 times pi times frequency times inductance, all that minus 1 over 2 times pi times your frequency times your capacitance. All that squared. Yeah, it's a funky little formula, but I'll put it on screen. Actually, I already did put it on screen, so you saw it. Indeed. That formula is a lot less scary when you realize you're doing multiple formulas at the same time. It's not one formula. You're really doing 3 formulas all at once. You're doing the formula for your capacitive reactance and your inductive reactance, and then you're getting your impedance. So 3 completely separate equations you're doing all at once to get impedance. So it's not as scary as it looks. And we did have a fun little thing that helped us, a mnemonic to help us remember which lags behind what. And it's kind of difficult to use, which is why I had to keep looking back. Honestly, I looked at a test answer that I got correct to be sure. Okay, am I remembering this right? I actually wasn't remembering it right, so good thing I checked. The thing is Eli the Iceman. That's we're knowing Eli the Iceman. What that is meant to mean is, in inductors, current lags behind voltage. Okay. And the idea there is inductors is L, current is I, voltage is E, but that would mean it's LIE. So you just kind of put the L at the middle point. So for inductors, so it's like current in inductors lags behind voltage, ICE. And then in capacitors, you have capacitor C now. In capacitors, voltage E lags behind current I. So you could say voltage. No. You could say current. No. Yes. Well, no, this whole thing is whack. Yeah, it's all whack because it just doesn't make sense, because we're getting LIE CEI, but it's supposed to be Eli Ice. I don't know. There has to be a way to write this. Someone knows, but Eli the Iceman is the way you're meant to remember. I'm going to rewrite it somehow and find some way to make it work, but it's still, like, it's just on screen here and it's like obviously incorrect. That's like, no, LIE and CEI don't spell Eli or ice. The letters are there to make it, but that's not what they spell. There must be a different way to do it. But phase, we went into phase. I spoke on phase recently in one of the final video logs I did for Introduction to Show Production, speaking about phase and polarity. It's such a stupid, simple explanation. And I had Miss Modulations explain it, but I really didn't need to. I understood it fine. I just didn't trust that I understood it fine, because I don't know, something about the way that it was taught in Introduction to Show Production was overly complex and confusing, and it didn't need to be. It really didn't need to be. It's very stupid simple. Polarity is the uppy bit versus the downy bit. Phase is entirely dependent on time. Phase is, are you a millisecond off this way or this way? A second, an hour, 15 years, whatever it is. Phase is about time. Polarity is about amplitude. Sort of. Amplitude is not the right word. Polarity is the uppy bits versus the downy bits. It's so simple. But unfortunately, the polarity button on a console isn't called that. It's called the phase button because it pushes it 180 degrees out of phase. But it doesn't. It doesn't do that. It does what that kind of could do, but it really just, it's a polarity switch. It's a polarity. Why are we calling it phase? It's not phase. And now I'm upset, and I'm one of those nerds that I was talking about from the previous video log who care about that stuff, because I care about it now because it's wrong. It shouldn't be wrong, but it is wrong. So just know, if there's a phase button on your console, it's likely not actually like moving your phase by 180 degrees. What it's really doing is it's inverting your polarity. It's a bloody polarity button. We should start calling it that. But then you get into the same argument that Alan and Heath have with their PAFL button. It's called a solo button. Yeah, but really it's a pre or after fade or listen, PAFL. But it's not the same sort of argument, because one's just bloody wrong. It's not a phase button, but it is a solo or PAFL. They're both correct. It's not a phase button. It's not. So I'm upset about it too now. Phase angle is what we're calculating. You can calculate what that offness is going to be, which is a function of your reactance and resistance. So, very similar. You can use those two to calculate your impedance. You can also calculate your phase angle. The function for that is the arc tangent, which is technically not true, but it's close enough to the inverse tangent button. So tangent to the power -1. Technically, it's not it. Technically, this is it. Thank you, Miss Modulations. But it's good enough, we've been told, for the equations. And just like I was saying previously with polarity, oh no, it's good enough. People who care about it are nerds. I might be a nerd next month and be like, no, it's absolutely not the inverse tangent button. No, arc tangent's different and it matters. And it probably does, but I don't understand why. Once I understand why, I'll be a nerd about it. But it's the arctangent of your reactance over your resistance. So take your reactance, divide it by your resistance, get the arctangent of that, that's your phase angle. Make sure you're in degrees mode, not radians. And that's used for, well, there's an example here. Hold up. Where are you at? Aha! That's used to find different types of power. So, first type of power we have is apparent power. That was the first thing we spoke on, which is the product of voltage and current at a given point. So any time in your electrical circuit. Another name for it is instantaneous or complex power. And the way you calculate that, which is measured in volt amps. So creative, volt amps. But it's straightforward at least, because it literally is just your I times E. It's your current times your electromotive force, which is your apparent power. It's very straightforward. You multiply your amps by your volts, and you get your apparent power. It's very straightforward in volt amps, which it's good that it's not creative, because that's honestly the best unit for it. It is a volt amp. It's the volt times amps. Yeah. Second type of power, reactive power. And these are not in any sort of like mathematical order of anything. It's just the way that it was brought up in class. So I'm bringing it up in a similar way. It's the same way. Reactive power, I don't have a good way to explain it. So sorry, again, mismodulations. Thank you. That is reactive power. And the way you calculate reactive power is you multiply your apparent power, was that right? Yeah, apparent power by the sine of your phase angle. So you get your phase angle, you get the sine of that, and you multiply that by your apparent power. And then you'll get your reactive power. So tells you, with it being in or out of phase from what you're wanting, which is not out of phase at all. I guess, and so that's not technically true. There are definitely moments where you want it to be out of phase, but mostly I'd imagine from a synthesis standpoint, not an electrical engineer standpoint, because I'm not one yet. I'd imagine you don't want a whole lot of phase shifting So you want a very low phase angle. But you can do that to get that. I think that's about it for what we had in lecture. So we had a lot of different example questions. So we had a lot. I pulled from one of them or two of them to kind of explain how this functions. Hopefully to get your head around it. If you basically understand the concept, you probably understand it a little bit better after this. If you don't understand it at all, you probably still don't understand it at all, because here I am explaining it to you and I'm still trying to learn it. Yeah. This class will have a lot of that. But it'll be fixed in the next video log where I'm like, oh no, I understand it now. Yeah. So there's that. That will help. And then Miss Modulation is being helpful as always. She can provide generalized information for us. So that's nice. Thank you, Miss M. Appreciate you. So that does it for the class stuff. C2A Business, we still have that giveaway happening. So if you are interested in getting a free SM58 dynamic vocal microphone and some Beats Studio 3s signed by me for free, shipping included, all around the world, just post a comment on that video. It's the 1,000 subscriber special. You'll find it if you go to my channel and you go to the pinned video. It's the pinned video. Yep. Actually, it's the pinned video for people who are not subscribed, I believe. For people who are subscribed, the pinned video is Cold Fire, which is the first ever original song I wrote. Yeah, so otherwise, you just search 1,000 subscriber special C28 music, and you'll find it pretty easily. It's the 5th episode of synthetic design, and the I guess 4.5 special of episode of Chaotic Death. I gotta make another one of those. I love Chaotic Death. Chaotic Death is a really fun series. Other than that, nothing. Still same stuff. Working on some songs, trying to get them released. We did actually, okay, one thing. We did get Dance of Dark Pixels released yesterday. So you can listen to that on Apple Music, Spotify, hopefully Tidal, preferably. They don't scam people out of their money. Lots of, distributors, but preferably people like Tidal who don't scam people out of their money. Do as you please, but use Tidal. Yes. Not getting paid to say that. They're just better. Let that sit with you. I haven't got much else for you, so I'm not going to hold you up. Yeah. Still working on mix and mastering. Control voltages, you can expect to see some behind the scenes stuff pretty soon on Lost Melodies and Unloved Timbers Volume 2. I think I'll do a behind the mix episode where I mix one of the songs live in front of you. I'll just have to figure out how to do the audio so that you can hear me the whole time. So I'll figure out a way to do that. But I think that about does it. So if you enjoyed today's content, you can subscribe. Little red button gives you content like this, more like it, from me and others. So go ahead and hit that little thing. Give it a friendly hug with your finger, poking it in the face. It's not how hugs work, but I think it's okay with it. Yeah. And then its friend, the join button, shows up. The join button, of course, lets you become a control voltage. Really cool thing. Get some cool perks. Firstly, you get access to the Discord server where the control voltages and I, legacy or new, will all get to chat and, just shoot the shit, have some fun, and plot for some videos. So if you want to get really engaged in that C2A community, control voltage might be for you. We'll see. You also get early access to videos, behind the scenes content, and more. Like I mentioned, control voltages, you can expect some behind the scenes content for mixing that new album. There you go. And that's about it for now. We'll figure out more things as we go. Trying to get a live done with the control voltages, but we'll just have to figure out how it works out, because we do have legacy control voltages in the Discord channel as well, which are people who are not officially, actually control voltages. We technically only have one official one, but they were control voltages from the previous era of this channel, so some of them were grandfathered in. They are legacy, and they get to join in the fun too for being legacy viewers. And a lot of mates of mine. Yes. So that does it for that. I hope you all take care of yourselves. God be with you. And goodbye, YouTube.